So today we're going to go over a problem called redundant connection, and this is LeetCode problem 684. In this problem, a tree is an undirected graph that is connected and has no cycles. The given input is a graph that started as a tree with n nodes with distinct values 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge that already existed. The resulting graph is given as a 2D array of edges. Each element of edges is a pair UV with U less than V that represents an undirected edge connecting nodes U and V. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the given 2D array. The answer UV should be in the same format with U less than V. And in our example 1, we have an edge going from 1 to 2, 1 to 3, and 2 to 3. The output is 2 to 3, and you can see from the photo here that in example 1 that we don't need the edge from 2 to 3. In example 2, the graph clearly shows how the edges are laid out: 1 to 2, 2 to 3, 3 to 4, 1 to 4, and 1 to 5. And you can see clearly that removing edge 1 to 4 will allow the graph to still remain as a tree. And if there are multiple redundant connections, return the one that appears earliest in the list. Okay, so let's go over to our whiteboard here, and here we have example 2 laid out, and as you can see, this is our graph here that represents the edges. So let's just go through our algorithm here. So we got a graph that's just going to be like this. We have a visited set, and basically we're gonna do BFS. We're gonna do DFS as a strategy to find the redundant connections. So we got our visited, and okay, now we're ready to start. And in our algorithm, we have for each of the edges, you basically do a DFS. And the reason why a DFS would help us find a redundant connection is that if I can get to an endpoint from a starting vertex, if I can get to an end vertex from a starting vertex, other than a direct edge connection, basically by traveling through another path in the graph, then that edge is a redundant graph because there's a path within the graph to go to that end vertex. So I'll just draw it out here. So we got, from our edges, we have 1 to 2, 2 to 3, 3 to 4, and 1 to 5. And we also have another edge from 1 to 4. Now, we don't need this edge to go from 1 to 4. We don't need a direct edge to go from 1 to 4 because there's a path within the graph. By going this way, we can just go through this way at 1, 2, 3, 4 to get to 4. So this edge is redundant and not necessary. And if we had more redundant edges, we would still return 1, 4. If we have more redundant edges that were, let's say, just an ellipse, we had more edges in here, they were redundant, we would still return 1, 4 because it appears earliest in the edges list. So let's just go back on that. Okay. So we'll just go through our algorithm here. So for UV in edges, and edges is 1 to 2, 2 to 3, 3 to 4, 1 to 4, and 1 to 5. Okay. And then let's see. So first we just bring out our 1 to 2. That's our first one. And then U is going to equal 1. V is going to equal 2. And then we're basically saying if 1 is in graph, and our dictionary is basically empty right now. So this if condition is already broken. So we don't evaluate the rest of it. And then we graph U, add V, graph V, add U. So basically we add a 2 in here, and then 2 also has an edge going to 1. So you basically you're basically saying that 1 and 2 are adjacent to each other in the graph. And then and I'll just draw this out again just to give a bigger visual example. And then let's see here. So we're done for 1 to 2, 2 to 3. Just cross that out. And then U equals 2, V equals 3. If 2 in graph, this condition is already broken. Graph U, add V, graph V, add U. So graph of 2, add 3, graph of 3, add 2. So basically do this. And we're showing that 3 and 2 are adjacent to each other, and we could see that here, right? Okay. So let's go to 3, 4. U equals 3, V equals 4. And basically, if 3 in graph, 3 does not exist in our graph. 3 is not in the graph, so that condition's already broken. Graph of 3, add 4. Graph of 4, add 3. So, and then there we go. And just to save some space, I'm just going to start deleting this stuff. Okay, 1, 4 is the next element in edges. Okay, so U equals 1, V equals 4, and if 1 in graph, which it is, and 4 in graph, which it is, then, and if DFS UV, so 1 to 4, and yeah, now we're rolling into our recursive DFS. So if start equal to 1, not in visited, add to visited. Yeah, so basically we're in our DFS and we're on this first line here. So basically we add 1 to visited, and then if 1 equals 4, we know that's not true, so we cross that out. And then we have this interesting line here that says array is DFS neighbor target for neighbor in graph start, return any in array. And the any function in Python basically looks at an iterable and see if there's a true value in the iterable, and if there is, you just return true. So basically this array is going to do this DFS neighbor target for neighbor in graph start is going to create an array of booleans, and if one of those booleans is true, then the DFS is going to return true. Okay, so let's try this. So DFS neighbor target for neighbor in graph start, which is equal to 1, and this is equal. If we look in our graph up here, graph of 1 evaluates to the set containing 2, and then so we do DFS of 2, 4, and then it's a recursive call. So if 2 not in visited, add to visited. So we do that. If 2 equals 4, which it doesn't, and then we basically do DFS again for neighbor in graph of 2, which is 1, 3, and then we do DFS for 1, 4, and so since we already did that call, that was our starting call up here. It's gonna so if 1 not in visited, but 1 is already in visited, so this DFS call is going to end early. And now we go to the next element in the set, which is 3. So DFS 3, 4, and if 3 not in visited, add to visited, and then 3 equals 4 if 3 equals 4, which it doesn't, and then we do DFS for graph of 3, which is equal to the set 2, 4. Okay. And then let's see, so that means we do a DFS of 2, 4. And then if the thing is 2 is already visited, right? So short the DFS short circuits, it ends early. So if 2 not invisited, well, we can see here it's already invisited. So this call is going to end early. And then we do DFS of 4, and then we add it to visited, add 4 to visited, and if 4 equals 4, which it does, return true. And that's going to take us from up here. That's going to return all the way up to this call. So that call is going to return true. I'm sorry, up to this call. So that condition is going to return true in the if statement. So if we go back up the recursive call stack, delete the call stack. Sorry, just a sec. Okay. And so we meet this whole condition here. Now we return UV, which in this case is return 1, 4. And that is the output that we have right here. So there we go. We're done. Have a good one.